Okay, so here's your first video for Unit 8, the behavior of gases. We're going to title this 8.1-Pressure. And pressure is really interesting because it's got some fortune-telling properties, not fortune-telling, but future-telling prophecies that pressure can help us with. And we'll get to that a little bit later. And we do that through meteorology, so by predicting the weather. So we can make some predictions by taking a look at the pressure in certain areas. So first of all, in order to have a really good understanding of pressure, we need to have a little bit better of a concrete understanding of what gases truly are. So we're going to look at some of the properties of gases. And the properties of gases can be easily told. The story of them can be told through something called the kinetic molecular theory, which has about 3 different points that we want to talk about. So point number 1 is that gas particles themselves occupy no volume. So if you think about the particle of gas, whether maybe it's an argon atom, that argon atom we are going to assume occupies absolutely no volume. Now that's not completely true because atoms are physical things. They have mass. They do take up volume. But for our calculations and for our understanding, we want to just make that point, that they themselves do not occupy volume. We also want to assume that these gases collide elastically. So what that means is when they run into each other, they don't slow down. They don't lose their energy from one to the other. They just keep on bouncing off each other like perpetual bouncy balls that just keep going and going and going. We also want to assume that gas molecules do not attract or repel each other. So essentially, 2 oxygen molecules do not interact with each other. One O2 and another O2 are pretty much by themselves. Oh, and the fourth point, I forgot about this one, but the average kinetic energy of gas molecules is directly related to the sample's temperature. So the more kinetic energy a substance has, the more temperature. And kinetic energy is based on 2 things, mass and velocity, much more based on velocity. So if those gas molecules are moving faster, then they're going to have higher kinetic energy, and that sample of gas will have a higher temperature. So some other properties of gases that are interesting to note is that they expand to fill their containers. If you have a small balloon and it's got, let's say, I don't know, a liter of gas inside of it, and then you pop that balloon, that gas will then escape its container, the balloon, and it will expand to fill up its new container, which is probably the room you're standing in. And so it'll be the volume, the new volume of the gas will be super huge. Gases can also be compressed. So we can take them from a high volume to a small volume. The gases respond very quickly to temperature change. We notice this with the Erlenmeyer over the top of the candle. The gases inside of the Erlenmeyer flask, when the candle accessed them, heated up very quickly. Thus, the bubbling of the water occurred because the gases were escaping because they were moving a lot faster. And then finally, the big one, gases exert pressure on their containers. They're bouncing around, they're moving around very fast, and so when they're hitting their container, they're exerting pressure on that container. So just a diagram, molecular level diagram of what's going on here. We've got gas molecules on the left piston here. If we increase the volume of that piston, you can see that those gas molecules spread out more, and so they'll have a new volume. Okay, the pressure is high over here, so we've got high P. But over here, since the volume is bigger, we've got a lower P over here. Liquid molecules, on the other hand, if we try to do that, if we increase the piston, the liquid molecules are going to stay at the same volume. So that's one of the really big ways that we can show the difference between gases and liquids. So what is pressure? Defined as the measurement of the amount of force exerted over a specific area. And I can really explain that, these are the units, but I can really explain that by looking at 2 pictures. So here we have a dude, let's say the dude's 180 pounds, and he's standing on the ground. So is he applying a force to the ground? Of course he is. If you change the ground with your head, then he's applying a force to your head. You would certainly feel him standing on your head. And he's applying that force over a certain area. The area is the area of his feet, the bottom of his feet. Now I'm going to look at another guy of about the same mass. Now he's standing on one leg. So is he applying a force to the ground? Of course he is. But is the area with which he's applying that force the same as the first man? No. In fact, it's half. So, if I'd ask you to circle or to ask the left guy or the right guy, who is applying more pressure to the ground, what would you say? And hopefully you would say, that gentleman is applying more pressure to the ground, because he's got a smaller area that he's applying that force with. So that's kind of our simple definition of pressure. We could talk about pressure in physics class. We could talk about pressure in earth science class. Today in chemistry, we really want to focus on pressure as it relates to gases. So in specific, gas pressure is the force of the gases that are colliding on the walls of that gaseous container. And sometimes that container can be super huge, like the Earth, for instance. The gases on the Earth, so the atmosphere, are applying a pressure on the container, which essentially is the ground or the things around it. And you don't notice this at all. You don't notice the air pressure of our planet because we've acclimated to it. We're used to it. But I can assure you, if you go really, really high in a mountain, you will certainly notice the decreasing air pressure. It'll be harder to breathe. Your ears will pop. You might get lightheaded. You might get sick. All of those things are due to the decrease in air pressure. So how do we measure this pressure? Well, we use a barometer, and the picture on the right is an old school barometer. The barometer gives us a reading called barometric pressure. And essentially, the higher the barometric pressure, the more pressure from the air. So what are the units of pressure? Well, at sea level, barometric pressure is about 1 atmosphere. So folks, we're right next to the lake. We're pretty much at sea level. So our standard atmospheric pressure is 1 atmosphere. We're a little bit lower than that. We're usually like 0.98 or 0.99, but we're pretty darn close to 1 atmosphere. There are some other units that we can use to talk about air pressure or pressure in general. Kilopascals is the second unit. Millimeters mercury is the third unit. And torr is the fourth unit. And I'm sorry, there should be an equal sign here. So millimeters mercury, torr, kilopascals, and atmospheres are all units that we can use to help talk about pressure. Now, the one we'll talk about most commonly is probably ATM or atmospheres, but just know that those other terms are going to pop up, and we may have to do some converting back and forth. So, for instance, you may be given a pressure in kilopascals, but in order for your math to work out, you might need that pressure in atmospheres. So you might have to do a quick conversion, and these equalities are going to help out with that. So how does air pressure actually change with altitude? Because I had mentioned that before. Well, take a look at the graph. If you can explain that graph, then you should have a pretty good grasp on how air pressure changes with altitude. Hopefully you come up with the idea that pressure decreases as you increase in altitude. So altitude and air pressure are actually inversely related. As one goes up, the other goes down. So can you think of why this is? That's important. I'm not going to give you the answer now. It'll be on the Ed puzzle for you to make a guess, and then we'll talk about it a little bit more in class. So I said at the beginning of the lecture that we can actually predict the future a little bit with the understanding of air pressure. And that's where meteorology comes in. So air pressure actually helps us to determine wind direction and weather patterns. Hot air is always less dense, and so it rises, it goes up. On the other hand, cold air is more dense, and so it sinks. When cold air sinks, it'll rush in to fill the void left by the hot air, because the hot air is gone up, it's higher in altitude. This change in air, so this flow that we have going on, that's what we know as wind. The direction of the wind and the speed of the wind will affect the weather's movement. So that's how we predict the future. So if we see a weather system on one side of the United States, we're able to calculate and look at the wind direction and the wind speed, we'll have a pretty good idea of when that weather system is actually going to make it here into Wisconsin. Thus, we can predict the weather 4, 5, 6 days in advance. I know it's not perfect. No meteorologist is perfect, but they're pretty darn good. So this picture does a really nice job of showing that whole wind concept. On the left, you see cool air over land, and it's going to sink because it's higher in density. On the right, you see warm air over land. It's lower in density, so it's going to rise, so there's low pressure there. And air always flows from high pressure to low pressure. In fact, most all substances flow from high pressure to low pressure. You should have noticed that in our Kickstarter activity with the Erlenmeyer flask. The high pressure on the outside of the Erlenmeyer flask force the water up into the Erlenmeyer flask. Why? Well, because there was low pressure on the top of the Erlenmeyer flask. So there's Steve Bayline, Action 2 News, and you pretty much know everything that he knows right now. And, you'll probably be a meteorologist yourself. But one more thing. Weather changes, weather patterns. So not only do meteorologists allow us to understand when weather's going to come our way, but they're also going to allow us or help us figure out when weather's going to change, when it's going to get better, when it's going to get sunnier, and when it's going to rain. Typically, a lowering of the barometric pressure indicates bad weather. This is because when warm air rises, it mixes with cold. Warm air mixing with cold air, well, that's a pretty good recipe to form clouds. That warm air, which has water in it, allows that water to condense when it rises. The water condenses into clouds, and if there's too much of it, well, then we get some rain. An increasing barometric pressure indicates fair or steady weather. Why? Well, this is because cold air sinks. It fills in the warm air void. And if it's filling in that warm air void, then there's really no mixing going on, in essence, in order for there to be clouds formed at higher altitudes. So oftentimes you'll see on a weather report a diagram like this. So we've got a low pressure front and we've got a high pressure front. Okay? The lowering pressure in this case, as you can see, the low pressure actually moving out that high pressure, that's actually causing a lot of rain. Now, this isn't always the case. I don't always want to say that lowering barometric pressure indicates bad weather and increasing barometric pressure indicates fair or steady weather. But it's a pretty good assumption that if we see those things happening, that we're going to get those weather changes. So once again, you've got the power now of Steve Bayline. All right, so that's an introduction to pressure.